All right, so we have Travis Addair, co-founder and CTO at Predibase, which you can find at predibase.com. The taglines on the website are adapt and serve models, your cloud or ours, and also highest quality, fastest throughput LLMs deployed in your cloud. So with that, Travis, welcome to the podcast.
Thanks for having me, Ben. Good to see you again.
And today, what brings us together is this fantastic post, which I will link to in the episode notes out of Predibase entitled How Reinforcement Learning Beats Supervised Fine-Tuning When Data is Scarce. So today we'll focus on the broader topic of what people are calling reinforcement fine-tuning, so RFT, as opposed to supervised fine-tuning, which we will sometimes refer to in this discussion as SFT. All right, so Travis, I guess let's start at the basics. RFT, what uh, what specific problem or scenario is it being used for?
Yeah, so I'd say at a
So,
high level, oh yeah, go ahead.
so in other words, I assume that people have some sort of model, and so then what? What is the specific problem that they're trying to do?
Yeah, so I'd say that the problems that people have for RFT, reinforcement fine-tuning, are broadly similar to the types of problems that they had for supervised fine-tuning, but using a different approach, which is a reinforcement learning-based method as opposed to a supervised fine-tuning based approach. And I think that, the reason why we're starting to see this convergence on this new terminology of like reinforcement fine-tuning kind of comes back down to the fact that in some ways it's a merger of two different things that have existed in the LLM ecosystem for a while, which is the reinforcement learning based methods with like the supervised fine-tuning based tasks, right? And, historically, when we've looked at reinforcement learning and its role in the LLM landscape, it's usually been applied in this space that we call like reinforcement learning through human feedback or RLHF, which is mostly about aligning models to subjective, often human-based preferences, right? Which is like the model outputs multiple different responses and a human sits there and says, I like this one, I don't like this one. And then the learning process is to try to align the model to do more of what the human likes and less of what it doesn't like. Um, and methods for that, like direct preference optimization has become really popular for that as a means of getting that style alignment. But I think the main thing to emphasize with RLHF is that most of the time we're talking about subjective preferences. Like that's why instead of giving it a direct score of like right or wrong, you're saying I like this one more than this one, right? It's like a qualitative measure as opposed to a quantitative. If you contrast that with RFT, RFT is much more about, in my mind anyways, like objective tasks, right? Like tasks where there's like a very clear right and wrong or correct and incorrect. And ideally also some gradation between the two where you can say, give partial credit to the model when it maybe gets the first bit right, but then doesn't get it all the way right. So for example, if you think about a common use case that we see for RFT, which is code generation, like natural language to SQL or something like that, then you can definitely say there's an objective right or wrong answer, which is does the code compile and generate the expected answer if we have like a ground truth solution that exists. But you can also provide some intermediate grading, right? Where you say, well, it got the function name correct, it parsed correctly, it didn't execute, so that's not right, and obviously it didn't give the right answer because it wasn't able to execute without erroring out. And so then you might give it some signal of, hey, you're making progress, like you're directionally correct, but you're not all the way there, and the model can kind of learn to make incremental progress through that.
So our listeners are at this point, I would imagine many listeners are familiar with supervised fine-tuning, and when they would go down that path, which is basically they have some sort of foundation model, but the foundation model might be great at general things, but not for their specific use case or application. So I take it so RFT, reinforcement fine-tuning, is trying to do the same thing, which is you take some foundation model, it's great, but it's not quite good enough for what I'm trying to do. Um, so with that said, so like I said, supervised fine tuning at this point, Travis, is like a commodity, right? So anyone can do it now with services like yours and a bunch of other services where basically it's all you have to do is gather the data. Here's a set of label data, which is basically here's a prompt, here's the desired output, and so on and so forth. I don't know, a few hundred of those usually would suffice. So it's a well-known workflow. So what was bad about that workflow? So what was limiting about that workflow? Why can't we just keep that?
Yeah, absolutely. I mean, for sure, I think one of the things that we set out to do originally with Predibase was make the process of training and fine-tuning very easy, like error-proof. Like it would always run to completion, it'd run quickly, and you get a good model the other side. So mechanically, I think that's largely a solved problem on the supervised fine-tuning front. What's not a solved problem is getting a good data set for fine-tuning, and that's still the long pole that is the biggest limiting factor today for people getting good results is how do you curate a sufficient quantity of good labeled data in order to teach the model what you're trying to teach it.
So
And a lot,
there was a hack in the early days, which would you would go use a superior model, like one of the open AI models, to generate some label data, right?
yeah, and that's definitely an approach that we still recommend to people today if they say, like sometimes a company will come to us and say, I really like the performance of existing strong foundational model, but it's too slow or it's too expensive.
Right.
And a very common technique people use is a distillation-based method where they take the outputs of the stronger model and then they use it to fine-tune a smaller model that's much faster, right? And I think that's fine if quality is not your primary concern, but just speed. And that's fine in a lot of cases, but oftentimes the proprietary models are not actually good enough for the task, right? You can't go to production with it because the quality isn't where you need to be. And in that case, the distillation approach is not going to really get you where you need to go. You actually need to improve the label data quality fundamentally. And that today, there's no perfect solution for that. Like there are obviously some synthetic data and LLM as a judge kind of strategies that people have explored to try to.
Or what? So Travis, so even if you're willing to spend money with this one of these data labeling products, so I take it what you're implying is that even if you're willing to do that, maybe the label data you'll end up getting is too narrow, doesn't quite cover edge cases and things like that, right?
Yeah, absolutely. I mean, there are lots of reasons why people struggle even with data labeling companies. Sometimes this problem is so domain specific that it's very difficult to give a very clear specification to the data labeling companies about what exactly they want. And then, oftentimes the curation of that data is difficult as well. Like sometimes it can only come from, their users making interactions in the tool. And so that is a big limiting factor because maybe their users are domain experts or something, and the people doing the data labeling are not domain experts, right? So there are lots of reasons why it's difficult to get good quality data. And as a result, the biggest kind of thing that we can do on our side as tools and infrastructure trying to help people build better models is to lower that barrier. Because if you think about, I think we always use this analogy with machine learning of like thinking about how humans learn and so forth. And, humans can learn complex tasks even within very, very specialized domains without requiring millions of examples, right? And when you think about it, this is fundamentally because the way we normally do supervised fine tuning is we're inherently kind of treating it as a memorization problem. It's like you compute the loss on what the model generates based on its exact match to a reference example. So you're basically saying like, unless you generate exactly what I have here in the solution, you're wrong. And if you have a single token wrong, you need to fix that, right? But that's not necessarily the case in the real world, right? It's like if you're generating code, what variable names you choose to use is not particularly important in terms of getting to correctness, right? And there are lots of things that can vary about different coding solutions that still lead to the right answer. And you might even have an LLM capable of generating a faster, more optimized solution than what your ground truth has. And in those cases, you don't want to penalize the model for diverging from what you reference as the right answer, right? You want to be able to give it the space to be creative and find these more sophisticated solutions. That's also true in the case of reasoning models, right? Like I think one of the reasons that we're talking about reinforcement learning today is because of DeepSeek and the DeepSeek Zero part of the paper that they released and the model that they released, and the fact that they were able to induce this aha moment, as they called it, where the model learned really sophisticated reasoning strategies through pure reinforcement learning. And the really interesting thing about that to me is that you really couldn't have supervised fine-tuning your way into that, right? It's like unless you knew exactly the reasoning process that would lead to that, um, the model could only have discovered that on its own. And that's really the necessary component to get these models to be able to do better than what we can directly specify them to do, right? Is to be able to give it the space through reinforcement learning to explore these more sophisticated lines of thought.
So obviously, the idea here is that now we'll start seeing services like yours that will allow people to do reinforcement fine tuning, right? So moving forward, just like as I alluded to, supervised fine tuning has become kind of a commodity at this point. But one advantage of supervised fine tuning, Travis, is somewhat easy for AI teams to understand what it is, right? So which is basically here's a model. I gather some labeled examples to improve it. I upload my labeled examples, go away, and then I come back with a fine-tuned model, right? So what, what would be, how would you explain reinforcement fine-tuning to a developer, and specifically, what do they need in order to make it work well? And I assume the workflow will at some point mimic the supervised fine tuning in the sense that they'll rely on services like yours, and a lot of the details will be hidden under the hood. But I guess to reassure our listeners a little bit, give us a peek into the underneath the covers to get them a sense of what's happening.
Yeah, well, I think the good news is that from my experience training a lot of models with SFT and training a lot of models now with RFT, I actually think the workflow for doing RFT is a lot more fun and kind of novel than SFT. So, as we discussed, SFT, you just give it a bunch of demonstrations of like, here's the input, here's the output, and typically you need thousands, tens of thousands of these, can even be hundreds of thousands if the task is sufficiently complex, right? With reinforcement learning and reinforcement fine-tuning in particular, what you really need is to think about the process a little bit more like your role is not to provide demonstrations, your role is to provide critique on what the model is doing. And so you can kind of think of yourself a little bit like a teacher in a classroom looking at different students' papers or solutions to tests and grading them. And obviously, one way you can grade them is to just say right or wrong, like this answer is incorrect, this answer is correct. But a good teacher might also go line by line through their solution, like if it's a math problem, for example, and say, hey, here's where you got it wrong. Like you should have done this instead. Or, you got these three parts right, but these other two parts were wrong. And so you need to go back and correct that. And giving it that nuance allows it to learn a lot more clearly, like and incrementally about what it should be doing. So
But I was a professor before. I hated grading a lot of papers. So how many papers are we talking about grading here?
yeah, well, I think that's the good news from my perspective as well, is that one of the original claimed benefits of this from some of the literature was that it's what we call a lot more sample efficient than supervised fine tuning. So, if supervised fine tuning requires thousands, tens of thousands of examples, RFT can often require just 10, maybe a dozen or so, up to 100 examples, depending obviously on how much breadth there is in the problem space that you're trying to get it to learn. But we published some work in our blog post that demonstrated that even with just 10 examples, you could provide meaningful lift over the baseline model, both with and without using chain of thought reasoning. And what I think is particularly interesting about that is that oftentimes we were to do this with SFT, it would just overfit, right? It would just memorize those examples and you try to run it on a held out test data set. it would completely blow up. And we saw that in our results as well. Like we tried doing SFT with 10 examples and the performance got worse, right? On a held out data set because it was just memorizing those examples. But with RFT, because you're never explicitly giving it the right answer directly and asking it to memorize it, even with 10 examples, it does a really good job at generalizing. And there was some, work done recently as a paper, I think, called SFT memorizes, RL generalizes, something like that. And they demonstrated the same thing, which is, you give them all a few demonstrations and it actually can learn the underlying mechanism much better than SFT and avoid getting into this trap. So just 10 examples, you're able to get started. Obviously, more data is better, but you really don't need a lot to get started.
So in the coding example, let's say text to SQL, right? So it is something that is easy to understand. Uh, you would just go, here's 20 examples of what I want from a query, and then what? It's not like supervised fine tuning. In supervised fine tuning, I would actually give it the SQL statement for each of
Mhm.
those 20, right? So what are we talking about here?
Yeah. So in one sense, you can think about the data set for RFT being the same as SFT as one option, right? So you can always say, I want my reinforcement learning process to have the same objective as SFT, which is exactly match some ground truth. But the nice thing about RFT is it can also be more flexible than that. So coming back to the natural language to SQL use case, let's say you don't actually have the ground truth SQL query that you needed to run, but maybe you do have the output that you expected to generate, right? I don't like the user says how
Oh, I
many.
see. Right. So the report that the SQL statement would generate, you have a sense of whether or not it makes sense.
Right, right. So another use case that I really like as a point of comparison here is in our blog post, we talk about this PyTorch to Triton use case, where it's like you have some code written in one framework and you want to translate it to a different framework. And what's nice about transpilation is that if you have an interpreter for both frameworks, then you can just execute the source framework code and execute the destination, the generated code. And if you have a test case, you can run both of them, right? And then look at the outputs and verify that they're the same. And in this case, you don't need any other data except the original source and the test case, right? Because whatever you generate, you can just execute it and compare the outputs with the original. So I think that's, and
And,
oftentimes, oh,
and,
yeah.
and assuming you have the ability to verify or provide this level of feedback, let's assume that for now. So how many examples usually would you need? I
Again,
guess
like
that's
this
a
is
hard question. It depends on the application, right?
Yeah, yeah. But
Yeah.
again, I would say, something like 10 is probably enough to get you started. What really matters here is that how much nuance is there to the problem, right? Like if in 10 demonstrations you can cover enough of the key characteristics that it can learn the syntax of the language you're trying to teach it, etc., then that might be all you need. But you can obviously, depending on how complex the problem is, like layer on more and more advanced scenarios. And you can think of this a bit like a curriculum in school, right? Where if you're trying to teach someone algebra or just mathematics in general, like maybe you start with the very simple stuff like addition, subtraction, and then once they get that foundation, then you can layer on more and more complex types of topics that you want them to learn. And so this is something that we observe playing out in reinforcement learning as well, is like oftentimes what's most efficient for the learning process, like if you're trying to teach a new programming language or something like that, right? Is you start with some very simple hello world style examples, and that gives it an opportunity to learn what's the basic syntax. And you can have some reward functions that you write that maybe use like a syntax tree parser or something like that to verify that the code it's generated follows the syntax of the language, etc. But then there are probably more advanced things you can do with the language as well, right? Like maybe there's closures and monads and whatever the heck else you want to do. And in those cases, you probably wouldn't want to give that as the very first thing that you're teaching the model, but you would want to be able to introduce that over time as it starts to learn more and more of the foundational concepts of what you're trying to teach it. So, all that being said, you can probably teach it some very basic things for almost any problem with just a handful of examples. And then from there, scale up the amount of data that you're teaching it, that you're presenting in order to teach it the more complex things that you want it to be able to grasp.
So many of the examples we've talked about seem to be in the realm of programming languages or tech, right? So let me ask you something slightly different, but something familiar to people who are doing NLP, right? So let's say I want to do an entity extraction, right? So, because I happen to have done this in the fine tuning sense, in the fine tuning world, right? So, I would want it to extract certain entities in let's say company names or whatever, right? And I would fine tune a llama model to do that well for certain class of companies, right? So can I do that in RFT?
Yeah, absolutely. And I think this is another case where the fact that you're able to give partial credit and so forth to the model is a nice benefit over doing this with SFT. So we definitely see people trying to do use cases like this with SFT. And if it's not an overly domain specific task, then sometimes it works pretty well. But what's nice about RFT is that you can write this reward function. So this is like, again, this grading concept, like this is the crux of like the entire learning process from your perspective as a user is you got to write these graders to say, okay, this was what the model generated. Was it correct or not? And how correct was it? And the nice thing about NER tasks or kind of JSON extraction tasks in general is that what you are given is an object that has one or more fields in it, right? And so each of those fields can be assessed for their correctness independently, right? So you could say, address, name, et cetera, phone number, and you can go line by line and say, okay, phone number is correct, address was incorrect, therefore I'm going to give this result like a zero point 0.2 out of 1, right, in terms of its reward score. So you got part of it right and you got part of it
And
wrong.
how many of these do you need to do?
How many of these reward functions?
Yeah, yeah. How many examples do you, how many examples do you need to grade in detail usually?
Well, again, what's nice about the grading is that I should specify is you don't have to manually grade every example, right? So usually the way that you would do it is you'd specify it as a function, which is like, here's an output that was generated from the model, and then you have some data that was in your data set that's maybe like the ground truth answer or something like that, right? So like in the NER example, your reward function is given what the model generated and what the ground truth was. So then what you can do is you can load the ground truth example into a Python dictionary, for example, and then iterate over every key in the data in the dictionary, and then parse the generated output into a dictionary as well, and compare and say, okay, this is the key that was in the ground truth, maybe address. Does it exist in the generated answer? If so, does it match, right? And then you can also maybe define different rules around matching, like maybe it has to match exactly. Maybe if it's like a location, you can have a little bit of fuzziness on matching, like maybe saying California and CA are the same thing for the purposes of what you're doing. Right. So these are all automated rules that you're specifying, right? So it's not like you as a human necessarily going in there and like explicitly looking at every example yourself, but you're just writing this rule-based system to determine whether or not the answer is correct based on some data that you have, right? And again, like this is, you're comparing to ground truth in this way because it's you have it. But if you don't have ground truth, then you could also imagine other ways that you could try to write these graders, right? For an extraction task, it's a bit harder because you have to know what needs to be extracted. But for a generation task, it can be easier as long as you have some,
So,
automated.
Travis, this grader for an extraction task can be as simple, but it can also be much more complicated, right? So, in other words, simple meaning every piece of text I pass you, I'm expecting that there will be a company name and the address of the company in there. And so then I can say, at the simplest level, whatever you produce should have those two things.
Mhm.
And then slightly more complicated, whatever you produce should have a company name, and the address should generally have a zip code.
Mhm.
And then you get more and more complicated after that.
Mhm.
So in essence, you're not actually producing examples, labeled examples. You're constructing a more and more sophisticated verifier or grader.
That's right. Yeah. And what you're describing there, we typically call like the formatting reward function, right? So you're trying to make sure that it's following the structure you're looking for. Like if there's an address field, the address looks like this, right? Now the one thing that isn't captured by a reward function like that would be the potential for hallucination, right? Which is, does the model generate a valid looking address, but the address is just completely wrong? And so that's where you would need some other type of grader on top of it for correctness to say, how do I know it didn't hallucinate? One way you can do that, of course, is you can have ground truth that says, here's what you should have generated, does it match? If you don't have that, because again, label data is hard to generate, what else can you do? Like there's other methods like LLM as a judge, where you have another LLM say, this was the input, this was what the model said. Is this consistent, right? Is this correct? And again, that's, not always going to work because those models can also hallucinate. But if it's a very strong model, it might do pretty well. And generally, models are better at these discriminative tasks, like saying if another model is right or wrong, than they are at generating answers themselves. And then finally, there are also like rules-based heuristics you can use, like say, okay, was this address actually found in the source document? If not, then it's almost certainly been hallucinated. But that also has error potential because multiple addresses could be in the document, right? So
So
us,
it sounds like Travis that a lot of innovation. There's a lot of room for innovation on the UX side for constructing these verifiers, right? So for someone with domain expertise, but maybe not super technical, but really knows the domain to really have a hand in constructing these verifiers, right?
for sure. Yeah. And I think this is like a big part of what we're trying to do on the platform side is precisely make this UX simpler. I think there's maybe three different fronts I would say that companies like us are going to try to tackle this problem from. One is on the efficiency side. So, can we train these models quickly and cost efficiently so it's not something that takes weeks? You want to bring that down to like, can it take minutes and hours, right? That's always the goal. There's also the quality side, like what can we do on the algorithm side in order to make this give you better results at the end? And some of what I talked about earlier about thinking about the data we choose to train on and when we choose to train on it. Do we start with easy things and work up to harder things? That's a big part of what we're thinking about and building into our platform as well. And then
So
to your
it's not when you say algorithm, you're not talking about the specific, because even on the RL side, there's PPO, there's GRPO, and so at this point, you just fix the RL algorithm, kind of like how people fixed LoRa in some ways, right? So and then do other things.
Yeah, so definitely, there's probably a lot of room to innovate on the algorithm itself. I mean, DeepSeek, of course, they produced GRPO, which was a simplification of PPO that's a lot more stable. And that I think in and of itself is the kind of innovation that would be valuable for platforms like us to be able to do. But I also think it's important to note that the tricky thing about to get right is always the data, right? And so I actually think most of the value is going to come from optimizations around how and what data we use in this training process. So like when we choose to use certain data, like what data we remove because it's bad, or what data we try to get more of because it's good, right?
Yeah. So Travis, in my reading of some of the papers in this field, not just the DeepSeek one, uh, while we fixate on RL, it seems like a lot of these papers make the point of saying that, hey, actually, SFT and RFT can work hand in hand,
Mhm.
right?
Absolutely.
So
Yeah.
when you have a little bit of label data, you can use it, right?
Yeah, absolutely. Well, I think that where SFT is valuable, and this was kind of proven out in the DeepSeek paper with the difference between R10 and R1, is really addressing this cold start problem
Right.
where the model is not particularly tuned towards the specific task that you want it to do. Then sometimes you can give it some strong baseline reasoning to work from, and then have it like do self-discovery through reinforcement learning afterwards, right? Um, and a common way that people do this in practice is they'll take a strong open source model like R1, and for R1 you can get its entire reasoning trace, right? It's not like hidden behind
Yeah, yeah. For our listeners, R1 is different from the proprietary models that do reasoning, like the ones from OpenAI and Gemini, in that I believe R1 actually spits out its reasoning tokens, right?
yes, exactly. And so I think this is, one big, obviously we're big open source proponents at Predibase because we build on top of open source foundations and open source models. But I think one of the big selling points of open source reasoning is that, a lot of the proprietary solutions try to hide the reasoning because they specifically don't want their competitors to distill the reasoning to train their own models, right? Which also makes it more difficult for you as a user to be able to make use of those models to distill smaller models. But with the open source models like R1, you can get that raw reasoning trace, so like the exact thought process that the model had, and then use that through supervised fine tuning to create a kind of baseline reasoning model for your task. Like maybe, prompt the model with something like 10,000 inputs, 1,000 to 10,000 inputs for your particular problem, get a nice distilled data set. You can also do techniques like rejection sampling to then go through the answers that were generated and like weed out the ones that are not good or not correct. Again, if you have a verifier, this is something you can do automatically.
But Travis, the reality is most enterprises won't have the sophistication to go that level of detail, right? So the best they can do is and hope is that companies like you will do that for them, but that you would develop better user interfaces so they can really help you on the verifier side, right?
Yeah. Well, yeah. And I guess like one thing I'd point out is we actually do have all the tools you need to do this entire workflow. We actually
Yeah.
recently did some work demonstrating this where we were able to distill R1 to train a speculator, which is a component that can speed up the inference process. So basically what we did is we took the reasoning trace for a very specific task, prompted R1 to generate, some thousand demonstrations of that, including the reasoning, fine-tuned the speculation model using that distilled reasoning, and then demonstrated that we were able to get like 50% to 2x speed ups over the baseline, like after doing this reasoning distillation. And we recently launched a batch API for Predibase as well, which is perfect for generating distilled reasoning. So you can say, here's my 1,000 or 10,000 inputs and just go generate your reasoning process for each of those and write it out to this file in S3, and then we'll go and use that to train a model later. So all of this can be done in just a few API calls pretty simply, right?
Going back to what I was kind of surfacing earlier, on the SFT side, SFT can now be done by a domain expert who's not technical at this point, right? So RFT at this point, do you feel like the user interfaces are still not there so that a domain expert can go in and do RFT?
Yeah, so I do think that UX is a big challenge with the tooling today, and that's precisely the problem we're trying to solve with the platform that we're building and launching for RFT.
So
And
what imagine fast forward 6 to 12 months, what would be your dream UX for RFT?
absolutely, well, I hope it'll be what we are launching with Predibase.
Yeah.
But maybe to summarize a little bit, I think that this idea of being the domain expert and
Yeah.
injecting your domain knowledge into the model, like I think you touched on a really good point here, which is that part has to be simple.
Mhm.
And, writing reward functions is not the hardest thing in the world, but it is a technical problem. But the nice thing is that you can simplify it to just some human, like, generated criteria, right? It's like the formatting must look like this. The answer must match this
So
thing.
they would write that out in natural language.
Yes, so that's one of the things we're working on is making it so that you can either specify it directly in code or you can specify it in natural language, and that those things will, depending on like what level of sophistication the user is, they'll be able to go with either
So
approach.
this is a very different task for a user who in the SFT realm would be tasked with labeling data or giving examples, right?
Right, right. So in this case, you'd still maybe have someone responsible for generating examples, you just don't need to generate as many of them. And then most of the effort is going to be on generating these reward functions because once you start training, like let's say you write your first reward function, you start training, you're going to see how the reward is changing over time, right? So this is normally how we would measure the loss typically for supervised fine-tuning. Like now we're measuring what the reward is over time.
Hey, Travis, what about this? So what if you give the domain expert the following, right? So which is basically, what task do you want to do? This is what I want to do. So then you you send that task to a model, and the model spits out, 20 examples or so. They're all wrong. And then that's the starting point for the domain expert. And the domain expert can say, hey, this answer is wrong because boom. And then is that a reasonable workflow for a domain expert?
Essentially, yeah. Only the one caveat I'd say is that, you have those inputs, so you're able to get the model to generate some answers. And instead of,
The inputs being just prompts of the domain expert, right? So
exactly,
yeah.
right, right. And so the prompts are there. And then I would say that instead of asking them to like hand critique every prompt individually, if you can just establish what the rules are that you're going to use, that would be the normal way that I would
But
imagine.
then having those 20 wrong answers would allow them to come up with those rules, right?
Yeah, I see what you're saying. So you might not know in advance what the rules should be
Yeah, yeah,
until.
because you don't know how bad the models are, right?
Yeah, yeah. Well, this actually, I think, to my point, one thing that I wanted to emphasize is that in our platform, this is actually a problem we're trying to solve for. So I'll like lay out exactly what
Yeah.
what we're doing, and so that'll give you a sense. So yeah, so the user first is going to write some reward function. All right. And initially it's going to be like a 0, 1 reward, which is did it get it right or did it get it wrong? Like, does the thing compile and give you the right answer? It doesn't match the ground truth, whatever, right? So you start training, and at some point you're going to notice that it's not learning very efficiently. Like the reward is not going up as quickly as you want it to. So what do? So in our platform, what we're going to provide is the ability to visualize exactly as you were saying, what the model is actually spitting out at every step and compare it to how that's evolving over time. So if you go back like one epoch or two, et cetera, and you can diff like, okay, it started here and now it's here. And you can tell if it's getting stuck on something, right? Like maybe it's learning like some basic syntax or whatever, but it's not getting it right because it's always using the wrong variable name or something like that, right?
But
Then
this is
that's
completely no code, just through a user interface,
through a
right?
user interface, yeah.
Yeah.
And this then gives you some intuition as a user about what the model is getting wrong. And so then you can go back to your reward function and say, all right, use the variable name blah 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 because that's the variable name you need to use, right? So you can give it a very explicit reward signal to say, for the thing you're currently getting wrong, go and fix that.
And this is
And
all natural language.
natural language or code.
Yeah.
So you can have a way of doing code, and we're working on a way of doing natural language as well. But once you've modified that or added that reward signal, that can then be dynamically updated in real time. So the training process gets that new reward function, and then boom, you instantly see how that affects the training process. So suddenly it goes from, being able to like not to make some progress, but getting stuck on this one thing to, oh, it's able to overcome that hurdle that it had and starting to learn again. And so as you're going through this process, you as the user are monitoring this history, this evolution of the model's generations, determining where it's getting things wrong, using that to update your reward functions, and then helping it get unblocked at every step of the process. So it's very interactive, but it's exactly, I think, to your point, what you want to do because, the model is not just a static point in time. You wouldn't just prompt it once, grade its responses, and then, call it a day. It's going to learn to do something, right? It might actually learn to do the wrong thing. Like, so for example, there's a common, the equivalent of overfitting in the RL world is what we call like reward hacking, right?
Mhm.
Which is where the model starts to get a strong reward, but it's doing so in a way that is cheating, right?
Right.
And an example of this came up in our PyTorch to Triton work that we did, where, we're trying to get the model to uh, take its PyTorch code and rewrite it in this Triton framework. And what it was doing is, at one point, was um, solving the problem in PyTorch and then writing a Triton function that basically did nothing and then just returned whatever the PyTorch code did, which is completely not what we wanted to do, right? We wanted to not be writing PyTorch code at all. And so what we did is we then had to go and modify our reward function again in real time to say, okay, let's now do a monkey patch. So like in Python world just means like replace the function with a different function. So replace the Triton function that it wrote with a no op. So basically just take the input and then return it back to the user and determine if the pre-monkey patch and the post-monkey patch code results are different. And if they're different, then we know that the function, that Triton function is doing something. If they're the same, that means there's likely reward hacking going on because it's trying to skip the hard part of the problem entirely, right? And so that's the kind of thing that you would notice if you're looking at what the model is generating and then going back and updating your reward function to respond to the things that it's cheating on or the things it's failing to properly understand about the problem. And that's, I think, what's different from SFT is in SFT, it's much more like, fire and forget, come back a few hours later, and then the model is either good or it's bad. But with RFT, you have that ability to kind of inject yourself in real time into its thought process and make corrections.
So if I were to summarize our discussion, it would be the following, right? So the good news for companies and enterprises is uh, foundation models are getting better. They're starting to get better at reasoning. Um, so the starting point for companies now uh, is much wider in terms of you have the models that can reason and the models that may not be optimized for reasoning. And that means for companies, you know, your starting point for the models is stronger, but that doesn't mean there's no need for you to customize models. And what we've been discussing here is the fact that the process for customizing models, you have another tool in your toolbox, which is RFT. So it's not that SFT is bad and it's going to go away completely. As we discussed earlier, actually, this SFT and RFT will go hand in hand. And what you'll need moving forward are platforms, I guess, like Predibase, that will allow you to customize your model. And when in the future, I imagine, Travis, when you're customizing your model, you actually don't care what you're doing, if it's SFT or RFT. You're just following the workflow of the model customization tool, which is maybe the workflow of the model customization tool in the beginning will ask you, hey, give me 20 examples. And then, hey, help me with this reward function or verifier, right? So at some point in the future, a domain expert will just be customizing these models, some of which can reason, some of which cannot, and they will use whatever is necessary in order to get the level of accuracy and performance they need for their domain and application, right?
Yeah, absolutely. I mean, to your point, I don't see SFT going away. It's like there's a lot of use cases where it's very beneficial. I think what RFT is interesting for is that there are a lot of use cases SFT was just not very good at, right? And those are cases where you don't have a lot of data, or you don't have a lot of labels, maybe a lot of inputs, but not a lot of labels. Or if you're trying to improve the reasoning of a chain of thought reasoning model. In those cases, SFT is just not a very good fit, right? Because SFT requires, typically thousands of demonstrations to be effective, depending on the difficulty of the task. SFT requires labels. It can't work with these kind of verifiers that RFT can. And for reasoning tasks, SFT can be used to teach a model like a specific style of reasoning from a stronger teacher, but it cannot be used to organically discover novel reasoning, right? Because it's not able to explore the search space in that way. So there are limitations, kind of a ceiling on how good SFT performance can be, right? Which is always bound by the quality of your labeled data. And that I think is what RFT is unique at unlocking is these newer ways of kind of going beyond what the current label data can do and discover like novel solutions, particularly for these complex code generation problems and reasoning problems and things like that, and to be able to do it with a small amount of data. That's, I think, the net value add here that is going to be very exciting in this year.
Yeah, yeah, and in many ways, it's natural, right? So if your universe of foundation models has broadened to now include these reasoning enhanced models, you need tools that will allow you to customize those reasoning enhanced models. So maybe your former tools were not do not lend themselves to doing that. By the way, Travis, before we end, I do want to drill down on one point, which is in the SFT world, right? So I collect the examples. That may take me some time, but at some point I just upload that, and then I kick off a service to do fine tuning, and it's not instant. I go to lunch, but by the time I go to lunch, usually it's done. So what is the timeline for RFT in terms of, let's say I have the verifier, how long does it take?
Yeah, well, it's very use case dependent, but I will say that RFT is today slower than SFT on like a step-by-step basis because you don't just have, forward pass, compute loss, backpropagate. You have, generate some number of examples, score those, forward pass on both the original model plus the new model, compute loss, backpropagate. So there's more stuff going on. It's more a complex procedure. But the flip side is because it's more sample efficient, instead of having 10,000 examples, you have to do this every epoch, you maybe have 10 examples. So you can, move faster just by virtue of not having to process as much data. So depending on the task, it can be, equivalent amount of time, or it can be longer if you have a lot of data. But our experience has been that, you should budget, probably a few hours to get this whole process to run for in general. And it's up to you if you want to have it run even longer, right? But that's the nice thing about tooling like Predibase is, you don't have to worry about, oh, if I close my laptop, it's going to crash or something like that, right? Or what to do if, there's like a transient failure. You just set it off, and once you feel like the reward function's in a good spot, you can step away for a bit, come back, see how it's doing. Maybe it's made some progress, maybe it's gotten stuck somewhere, make your adjustments. So as long as you're not, hoping for it to be done in a matter of 5 minutes, then it's pretty reasonable. But the thing I expect is that platforms like us will, continue to make this faster and faster to the point that hopefully it will get that fast someday.
And then obviously as the foundation models get more capable, let's say visual language models or some sort of multimodal capability, uh, AI teams all over the world will want to customize those models. And so I don't know. I think the space of customizing these models will move uh, just as fast as the space as the models improve, right? So I think the RFT, as you point out, arose because we have these reasoning enhanced models. So obviously, if you want to customize those, you have to add something to the way you customize models. So who knows? The multimodal models may introduce something, some new twist, and the mode for customizing those will need to adapt. And so, what you need, listeners, are platforms that can adapt with the changes in the foundation model space.
Absolutely. Yeah, I think that that's very well put. And the way that I think about it is that you always are going to want some customization because as a business, like these AI models are your IP, right? This is going to be what gives your company its edge over your competitors. And if you're just using the same foundation models that everyone else is, then you're at an inherent disadvantage, right? Because you're being commoditized. But if you're building a custom solution to your data through techniques like SFT and RFT, then that's how you create like differentiated value in the market.
And I think for me, Travis, what I've been telling people is, opt optimize for post-training. So assume that someone is doing pre-training, but optimize for post-training, and post-training includes all everything we've talked about and more, right? So
Absolutely. Yeah. I would say if there's one thing that came out of last year is that the pre-training days, I think, are behind us in terms of that being where we're going to get a lot of efficiency gains, both from a standpoint of the foundation model companies, but also from a standpoint of enterprises looking to build their own models. Like we don't see anyone in practice building models from scratch
yeah.
these days. The costs are just not worth it, and you can customize models through these post-training techniques to get the domain adaptation you need without having to spend millions of dollars, right? So it's like the economics have become dramatically more favorable to post-training, I'd say.
And with that, thank you, Travis. And again, I'll link to the article that was the basis of this discussion. And obviously, check out predibase.com.
Thank you, Ben.